So for our very final section of this course, we're going to very briefly look at radical reactions. Radicals, we've talked about them at times before, but radicals are species that are single unpaired electrons that are very, very reactive. And radicals are useful for, a large number of different reactions. The biggest problem with at least some radical reactions is that because radicals are so reactive, that in a lot of cases it's difficult to control their reactivity, and you can often end up with unwanted or undesired byproducts. Now, that being said, they're still useful for a number of things, and we'll see some examples here. Now, every radical reaction has three basic steps: initiation, propagation, and termination. An initiation step will generate new radicals. And specifically, it does that from non-radicals. So there's a number of compounds that are known as radical initiators, and they're ones that you can use under usually pretty easy conditions to form a radical when you didn't have one to begin with. An initiation step will, in general, increase the number of radicals you have present. The two most common ways to do this are either to have compounds that have very weak bonds in them and heat them. This is something that you can do with peroxides. You can break the oxygen-oxygen bond by heating it, and you end up with the two oxygen radicals. The other common way is with UV light. And this works quite well for halogens. So if you have something like bromine, you hit bromine with ultraviolet light, and it breaks apart into two radicals. So those are examples of initiation steps. Once you've formed your radical, then you can get what are known as propagation steps. In a propagation step, you have a radical reacting with a non-radical. And a propagation step keeps the number of radicals constant. It's steps like these that also often give these the names like chain reactions, because here, for example, we have a chlorine radical reacting with methane. The chlorine and the hydrogen each contribute one electron to form a new bond. The other electron goes over to the carbon, and we end up with hydrochloric acid plus a methyl radical. And then maybe that methyl radical could react with chlorine in the same way to form chloromethane plus a chlorine radical. And so you notice, first of all, in each of these steps, we started with one radical and we ended with one radical. And that's what allows this process to keep going, is that yes, a reaction's taking place, but we're still keeping a population of radicals present. The final step is known as termination, and this is the combining of two radicals. This is a step that always decreases your population of radicals. And in many ways, it's essentially the opposite of the initiation step. You could have two chlorine radicals, they each contribute their electron, and you form a new bond. Or you could get two methyl radicals. The termination steps are usually the least common because your concentration of radicals in solution at any one given time is usually very low. And so this process, this reaction that we've just outlined, this is how you can halogenate an alkane. We start with bromine. We break up the bromine-bromine bond or chlorine-chlorine bond. With UV light, we get the chlorine radicals. They can react with our alkane to form an alkane radical. That alkyl radical can react with another one of the halogens, and we get our alkyl halide to form. The biggest problem in this reaction is you often end up with issues of control, and you can easily end up with overhalogenation. Now, perhaps the most useful thing that we can do with radicals is to have them involved in a reaction that doesn't require a great deal of control. And that's for making polymers. So if we start and oxygen-oxygen bonds are great for forming radicals. They're generally weak bonds. We form a radical like that. And then we typically add alkenes, such as ethylene. And as you can see, when the alkene reacts with the radical, we form that new oxygen-carbon bond, and we're left with a radical at the end of the chain. And then it can happen again. And again, and again, and it keeps going. And in this case, we started with ethylene. This polymerization can go on, over 100,000 times. And this is how we make polyethylene, which, is commonly used for shopping bags. But with a number of other common alkenes, we can make a number of other, very, very well-known polymers. For example, if we take ethylene and put 4 fluorines on there instead of the 4 hydrogens, and we polymerize that, that's how we make Teflon. Or an aromatic ring on our alkene is how we make polystyrene or styrofoam. So when it comes to radicals, radicals actually have very similar stability to carbocations. Or in other words, the more substituted a radical is, the more stable that radical will be. Same behavior as for a carbocation. But interestingly, that doesn't mean that we get the same type of behavior as we do with carbocations. If you think about reactions, alkene addition reactions that went through carbocations, we pretty much always saw a preference for the most stable carbocation forming. Well, if we look at halogenation, say with chlorine, versus halogenation with bromine, we find two very different results. So we could get the halogen to go at that tertiary position, the more substituted position, the substitution that would come from the more substituted or more stable radical, or we could get it at the less substituted position. If we do this reaction with chlorine, we get a ratio of about 1 to 2, where the major product is actually the less substituted chloride. But if we do this reaction with bromine, we get over 99% for the more substituted product. Why is that? Well, the explanation, and as far as we're going to go to end this course, is to talk about what's known as the Hammond postulate. The Hammond postulate basically looks at the structure of a transition state. And it says that the structure of a transition state resembles the structure of the nearest stable species. So what does that mean? So let's just look at a couple of very, very simple energy diagrams. So here's an endothermic process, and you can see that the transition state is very close in energy to the product. So what the Hammond postulate tells us is that in this reaction, in this process, the transition state will look a lot like the product. Or maybe we have an exothermic process. Now we can see that the starting material is much closer in energy to the transition state. And so in this situation, the transition state will look very much like the starting material. And so what we find, and what explains that bromination-chlorination situation, is that in bromination, the transition state is very close to the radical. And so as a result, the transition state gets formed as the most stable radical, the most stable intermediate. But in chlorination, the transition state is closer to the starting material, and so it's more like a kinetic, or what is the easiest product to form. And so without going into a lot of detail about this reaction, that's sort of the simple explanation for what's going on here. And with that, we have now reached the end of Organic 2. Thank you.